This is where reinforcement learning actually starts for a lot of people. Reinforce. It is the oldest, simplest way to teach a model by trial and reward, and almost everything fancier is built on top of it. Think of training a dog with no manual. You let it try a whole bunch of things, you wait to see how the day went, and then you give more treats for the behaviors that led to a good day. That is the entire vibe here. So step 1, you let the policy, your model, play out a whole episode from start to finish. It picks an action, the world responds, it picks another, all the way to the end. You do not interrupt. You just watch the full story play out. Step 2, for each moment in that story, you add up all the reward that came after it. That running total is called the return. It is basically, how did things turn out from this point on? Good ending, big number. Rough ending, small one. Step 3 is the actual learning. For every action you took, you nudge the model to make that action a little more likely, and you scale that nudge by the return. So actions followed by a great outcome get pushed up hard. Actions followed by a flop get pushed up barely or pulled down. And why the log of the probability? That is just the clean mathematical handle for nudging a probability up or down. Do not let the symbol scare you. It literally means make the choices that paid off more probable next time. And that is it. That is reinforce. Sample a full trajectory, score each action by what came after, and push the good ones up. A Monte Carlo policy gradient, which is a fancy way of saying, learn from whole sampled episodes. Here is the catch, and the next question always pokes at it. Because you wait for an entire episode before learning anything, the signal is incredibly noisy. One lucky bounce can make a bad action look great. So plain reinforce is honest, but it is jumpy and slow to learn. And the thing that separates reciting it from getting the offer. Do not call it a loss function. Say it is a Monte Carlo estimate of the policy gradient, and that the return is what weights each action. When you frame it that way, the interviewer knows you actually get why every later method exists. So go code the loop yourself. Roll out an episode, compute the returns, take one update, and watch the model slowly start preferring the good moves. The free notebook is in the bio. So they let you explain reinforce and then they lean in. Okay, it works, but it is super noisy. Why and how do you calm it down? This is the question that quietly sorts the room. The noise comes from those full episode returns. You are judging every action by how the entire rest of the story went, and stories vary a ton. Same good move, one episode it rides to a win, the next it gets dragged down by stuff that had nothing to do with it. That swing is the high variance. Here is the fix in one image. Imagine grading a student on a brutal exam. A raw 70 out of 100 tells you almost nothing, but 70 when the class average was 40. That is a great score. You want to grade against what is normal, not the raw number. So instead of weighting each action by the raw return, you subtract a baseline first, a typical score for that situation. Now the model only reacts to the surprise. Did this do better or worse than usual? The everyday ups and downs cancel out, and the signal gets way steadier. And the usual choice for that typical score is a learned value function, written as the value of the state. It is a little helper model whose only job is to predict from here how good do things normally turn out. You train it alongside, and it gives you the bar to compare against. Now the part that feels too good to be true. Doesn't subtracting something change the answer? No, and this is the elegant bit. As long as the baseline does not depend on the action you took, the average direction of the update is exactly the same. You only cut the noise. You do not bend the truth. And that is the whole payoff. Same expected gradient, dramatically lower variance, so training actually converges instead of bouncing around forever. One subtraction, and reinforce goes from a cute idea to something you can really run. and the line that gets you the offer. Anyone can say subtract a baseline. The signal is explaining why it stays honest. Because the baseline is independent of the action, it has zero effect on the expected gradient, so you reduce variance for free. Say that, and they know you understand it, not just memorized it. So go run reinforce with the baseline turned off, then on, and watch the training curve stop shaking. That moment is when it really clicks. The free notebook is in the bio. This one is small, but it shows up everywhere in modern reinforcement learning. The advantage function. If you can explain it in plain words, a whole pile of later stuff, like PPO, suddenly makes sense. Here is the whole idea. Advantage answers one question. For this exact situation, was the action I took better or worse than just playing it average? Not was it good in some absolute sense. Better than the typical move from here. That is it. To get there, you need two values. The value of taking this specific action from this state, written Q of S and A, and the value of this state in general if you just behave normally, written V of S1 is the specific choice. One is the baseline for the spot. And the advantage is just the first minus the second. The value of this action minus the value of an average action here. Positive means you did better than the room expected. Negative means you fumbled relative to normal. It is literally a how much did this beat the average number. Picture a chess position that is already winning. Almost any move keeps you ahead, so the state value is high. You play a sharp move that is a little better than the rest. Its advantage is small and positive. You were in a good spot and you nudged it slightly better. The advantage isolates exactly that nudge. And here is why everyone reaches for it. Because it is already measured against the average, it naturally sits around zero. Good moves are positive, bad moves are negative, and the boring baseline is subtracted out. That is the cleanest, lowest noise signal you can hand a policy gradient. And that is the payoff. The advantage is the baseline idea from before, packaged into one neat function. Instead of pushing on raw returns, you push on advantage, so you reduce variance and the gradient stays honest at the same time. And the trap people fall into. They read a positive advantage as this action was good. Not quite. It means better than average for that state. A mediocre move in a winning position can still have negative advantage, and a decent move in a losing position can be positive. It is always relative. Miss that and the interviewer hears memorization. So the line that clears the bar. Advantage equals the value of the action minus the value of the state, and it measures how much better an action is than the average from that same state. Say relative, and say why that lowers variance, and you sound like someone who has actually trained these things. So go compute advantages by hand on a tiny rollout and watch which actions come out positive and negative. Once you see it, it never leaves you. The free notebook is in the bio. Okay, this one sounds intimidating and the name does not help. Generalized advantage estimation. GAE, but it is really just a smart dial for trading off two kinds of error. And once you see the dial, it is genuinely simple. Remember the advantage from before. There are two ways to estimate it and they fight each other. Look just one step ahead and lean on your value guess. That is steady but a little biased because your guess could be off, or wait the whole episode for the real outcome. That is honest but super noisy. Neither one is great alone. So here is the move. Why pick? Blend them. Trust the near future a lot since it is close and reliable, and trust the far future less and less since it is murkier. It is like planning your week. Tomorrow you predict pretty well, next month you barely guess. GAE bakes that fading trust right in. The building block is one little surprise signal at each step, called the TD error. In words, it is the reward you actually got, plus your value guess for where you landed, minus your value guess for where you started. Basically, was this step better or worse than I expected? one small honest correction per step. And the advantage is just a weighted sum of all those little surprises going forward, where each step out gets multiplied by a fading factor. The next surprise counts almost fully, the one after a bit less, and so on, shrinking smoothly into the distance. Add them all up and you have got your advantage estimate. And lambda is the dial that sets how fast that trust fades. Turn lambda to 0 and you only believe the very next step, low noise but biased. Turn it to 1 and you trust the whole future equally, which is just the noisy full episode version. So the two extremes you hated are the ends of one slider. And in practice people land around 0.95, close to fully trusting the future, but with just enough fade to kill the worst of the noise. It is the comfy middle of that slider, and it is why GAE quietly powers basically every serious PPO run. And the classic mix-up. People blur lambda with the discount factor gamma. They are different jobs. Gamma is how much you care about future reward at all. Lambda is how much you trust your own value estimates versus the raw returns. Say that distinction out loud because plenty of candidates cannot. So the framing that gets you the offer. Call it an exponentially weighted average of n-step advantage estimates, and say lambda trades bias against variance. When you describe it as one knob between the one-step view and the full episode view, the interviewer knows you have actually tuned it. So go implement GAE and sweep lambda from 0 to 1. Watch the advantages go from biased and calm to honest and jumpy, and feel where the sweet spot sits. The free notebook is in the bio. This is the idea that makes PPO practical instead of painfully slow. Importance sampling. And the question behind it is really, how do you stop throwing away expensive data after a single use? Here is the pain it solves. In plain policy gradient, you collect a batch of experience, take exactly one update, and then that data is stale because your policy just changed. For language models, generating that data is the slow, costly part. Using it once and tossing it hurts. The intuition is reweighting. Say you surveyed last year's customers, and this year's crowd skews a little younger. You do not run the whole survey again. You just count the younger responses a bit more and the older ones a bit less. Same data, reweighted to fit the new situation. And the weight you use is one clean number, the importance ratio. It is the probability your new policy gives an action, divided by the probability the old policy gave that same action. Bigger than 1 means the new policy likes this action more than the old one did. Smaller than 1 means it likes it less. So now you can take that one batch you paid dearly for and squeeze several gradient steps out of it. Each step, you multiply by the ratio to correct for the fact that your policy has drifted from the one that gathered the data. You are reusing experience instead of regenerating it. And that is the payoff. Importance sampling lets you learn off policy for a few steps, meaning you keep improving from data collected by a slightly older version of yourself. For something as expensive as language model rollouts, that is the difference between feasible and forget it. But there is a real danger, and it sets up the next card. If your new policy wanders too far from the old one, that ratio can blow up to something huge, and a single weird sample can wreck the update. So this reuse is only safe while the two policies stay close. That fragility is exactly why PPO has to clip. So the answer that gets you the offer ties it together. Importance sampling reweights data from an old policy so you can take multiple updates on one batch, and it only stays valid when the policies are near each other, which is precisely the problem PPO is built to manage. Say that link and you sound like you have shipped this. So go compute the importance ratios on a batch and watch them creep away from one as you keep updating. That drift is the whole story. The free notebook is in the bio. This is the one. If you are interviewing for anything touching RLHF, you will get asked to explain the PPO clipped objective. It is the workhorse behind tuning these models, and the formula looks scarier than the idea. Start simple. The basic goal is take the importance ratio from before, multiply it by the advantage, and push. Positive advantage, you raise that action's probability. Negative, you lower it. So far, this is just policy gradient with a reweight. The magic is the guardrail we add next. The problem is greed. If an action looks great, plain optimization will crank its ratio way up, way past where the data still supports it. One overeager leap in training falls apart. We want to encourage the good actions, but not let any single update yank the policy off a cliff. So picture a leash. You let the policy move toward better actions, but only so far per step. The moment it strains past a set distance, the leash goes taut and stops rewarding it for pulling harder. You still make progress, you just cannot bolt. That leash is the clip. Concretely, you take that ratio and you clip it. You trap it inside a little band around 1. Typically from 0.8 to 1.2, that is epsilon of 0.2. So no matter how excited the update gets, the ratio it is allowed to use is fenced in. Roughly 20% of wiggle room, no more. And here is the genuinely clever bit, the part people botch. You compute the objective two ways, with the raw ratio and with the clipped ratio, and you keep the smaller, more pessimistic one. That means the clip only ever holds you back. It never lets a step off the hook. It caps your upside but never hides a mistake. That is why it is stable. And that is the whole objective. Ratio times advantage, but clipped into a band and taken pessimistically with the minimum. You improve steadily without any single step blowing up the policy. Proximal, meaning you stay close to where you were. That is the P in PPO. And the part that gets you the offer. Lots of people remember the clip but forget the minimum. Explain that the min makes the bound one-sided, so it removes the reward for moving too far but still fully counts a bad move. Say that, and you have shown you understand why PPO is safe, not just what it types. So go code the clipped objective and plot it against the raw one. Watch the curve go flat past the band, and you will feel exactly what the leash is doing. The free notebook is in the bio. You wrote the clipped objective. Now the follow-up that separates people. Why clip the ratio in the first place? Not what does it do? Why does PPO even need it? This is the one where you either understand it or you are reciting. Go back to important sampling. Reusing old data is only honest while your new policy stays close to the old one. The further you drift, the more those importance ratios stretch, and the math you are leaning on quietly stops being trustworthy. Push too far and you are optimizing a number that no longer means what you think. And the failure is brutal. One action gets a wildly large ratio, the update treats it as gospel, and the policy lurches somewhere terrible in a single step. In reinforcement learning, there is no reset button. A bad lurch corrupts the very data you collect next, and the whole run can spiral. That is the nightmare clipping prevents. Think of tuning a recipe you already kind of like. You add a pinch of salt, taste, adjust. You do not dump in a whole cup because the last pinch helped. Small, checked steps keep you near something that works. Clipping forces the policy to improve in pinches, not cups. And there is a name for the region where your steps are still safe. A trust region. It is the neighborhood around the old policy where you can trust the update to actually help. Clipping the ratio into that little band around one is a cheap, blunt way to keep every step inside that region of trust. And that is the elegance. Older methods enforce the trust region with heavy, expensive math. PPO just clips a ratio. Same goal, keep updates small and safe, but so simple you can write it in a few lines. That trade, almost as good for way simpler, is why PPO took over. So the payoff of clipping is just stability. By refusing to reward any step that leaves the trust region, PPO keeps learning smooth and monotonic instead of explosive. You trade a little bit of speed per step for not blowing up. In RLHF, that trade is absolutely worth it. And the answer that gets you the offer connects the dots. Say clipping enforces a trust region in probability ratio space, and it exists because importance sampling only stays valid near the old policy. When you tie the clip back to why reusing data is fragile, the interviewer sees the whole chain, not a memorized fact. So go train PPO with the clip off and watch it detonate, then turn it on and watch it settle. Seeing the explosion is what makes the why stick. The free notebook is in the bio. Quick one that trips people who only learned PPO from one tutorial. There are actually two flavors of it. If you can name both and say when each is used, you instantly sound like you read past the first blog post. And both flavors want the exact same thing. Keep the updated policy from straying too far from the old one, so training stays stable. They just enforce that closeness two different ways. Think of it as two styles of guardrail for the same road. The first is PPO clip, the one you already know. It takes the importance ratio and just clips it into a band around 1, flatly refusing to reward steps that go too far. It is a hard wall. Simple, blunt, and it works. This is the version almost everybody actually runs. The second is PPO penalty. Instead of a hard wall, it adds a soft fee. The further the new policy drifts from the old one, measured by KL divergence, the bigger the penalty it pays in the objective. So it is free to move a little, but wandering far gets expensive. A toll road instead of a wall. And penalty can tune itself. It watches how far the policy is actually drifting, and if that is too high it cranks the fee up, if it is too low it eases off. So the toll adjusts itself to keep the drift near a target. Clever, but it is one more moving part to babysit. So why did clip become the default? Fewer knobs. The penalty version means tuning that coefficient and its adaptation, which is fiddly. Clip gets basically the same stability with one simple operation and almost nothing to tune. In practice, simpler and robust beats elegant and finicky. Now the trap that catches strong candidates. The KL penalty inside PPO penalty is not the same as the KL term you see in RLHF that pulls the model toward the original reference model. One keeps consecutive updates close. The other keeps the whole tuned model from straying from where it started. Same letters, totally different job. Mix them up and it shows. So the answer that gets you the offer is crisp. Clip uses a hard clip on the ratio. Penalty uses an adaptive KL penalty. Both keep the policy near the old one, and clip wins in practice because it has fewer hyperparameters and is just as stable. Say that and you have shown range, not a single memorized recipe. So go run both variants side by side and watch them land in a similar place, then notice how much more tuning the penalty one demanded. That comparison is the whole lesson. The free notebook is in the bio. PPO is often called an actor-critic method, and the next question is, fine, what is the critic even doing? If you only ever talk about the policy, you are telling them you understand half of PPO. There are two characters here. The actor is the policy, the one choosing actions, the part everyone talks about. The critic is a second network whose only job is to size up a situation and predict how well it tends to go. One acts, one evaluates, and the evaluator is quietly essential. Specifically, the critic learns the value of a state, written V of S, that is its best guess of the total reward you will collect from here on out if things go normally. It is the seasoned scout who walks into a position and says, this is about a 7 out of 10. And here is why it matters so much. Remember advantage, how much better an action did than average. The critic is what gives you that average. You take what actually happened and subtract the critic's prediction. Without the critic, you have got no baseline, and you are back to noisy raw returns. The critic is the thing that tames the variance. And how do you train the critic? Plain regression. It predicts a value, you compare it to the actual return that came in, and you push it to close the gap, squaring the error so big misses hurt more. Nothing exotic. It is just learning to guess outcomes a little better every batch, right alongside the policy. So the payoff is a feedback loop. A sharper critic gives cleaner advantage estimates. Cleaner advantages give the policy a steadier signal, and a steadier policy generates better data for the critic. The two lift each other. The critic is not a sidekick, it is half the engine. And the trap. People sometimes think the critic is what gets deployed or that it picks the actions. It does not. After training, you ship the actor. The critic exists purely to make learning less noisy, and then it steps off stage. Confuse those roles and the interviewer hears a gap. So the line that gets you the offer. The critic estimates the value of a state. It serves as the baseline for computing advantages, and it is trained by regressing toward observed returns, which lowers the variance of the policy gradient. Say baseline and say variance, and you have shown you get why it is there. So go train the actor and critic together. Then watch your advantage estimates get tighter as the critic learns to predict returns. That is the loop in action. The free notebook is in the bio. This is the one that tells them whether you have actually run PPO or only read about it. They ask, roughly what settings do you use for RLHF? You do not need exact magic numbers. You need ballparks and the why behind each one. And first, the right mindset. Nobody wants you to recite a config from memory. They want to hear that you know what each knob controls, so when training misbehaves, you know which dial to turn. So let me walk the handful that matter, and what each one is buying you. First, the clip epsilon, usually around 0.2. That is how far the policy is allowed to move in one step. Bigger means faster but riskier. Smaller means safer but sluggish. 0.2 is the comfortable middle, and you rarely have a reason to wander from it. Next, the GAE lambda, about 0.95. That is the bias versus variance dial from a couple cards back. Near one, so you mostly trust the real returns, but pulled in just enough to calm the noise. It is one of those numbers that is sticky for a good reason. Now the one people get wrong. The learning rate around 1 times 10 to the minus 5, even down to 5 times 10 to the minus 6. That is tiny, way smaller than pre-training. And that is the point. You are gently steering an already smart model, not teaching it from scratch. Too big a rate and you wreck everything it knew. Respect how small this is. Then how hard you squeeze each batch of data. Usually 2 to 4 passes over it, in minibatches of roughly 64 to 512. Remember, important sampling is what lets you reuse a batch at all, but only a few times because the policy drifts. 2 to 4 passes is the sweet spot before that drift bites. And a few smaller weights. The value coefficient, around 0.5 to 1, sets how much you care about training the critic. A tiny entropy bonus, about 0.01, nudges the model to keep exploring instead of collapsing to one answer. And if you use a KL term, roughly 0.01 to 0.1, to keep it tethered to the reference model. Small seasonings, but they matter. And the trap that sinks people. They grab a normal deep learning rate, the kind from pre-training, and plug it into RLHF. It is orders of magnitude too big, and the model forgets everything almost instantly. If you remember one thing from this card, it is that the learning rate here is shockingly small on purpose. So what gets you the offer is not the digits, it is the reasoning. Epsilon caps the step, lambda trades bias for variance. The learning rate is tiny because you are nudging a pre-trained model, and you only do a few epochs because the data goes stale. Say it that way and they know you have debugged a real run, not skimmed a table. So go run PPO and poke each knob on purpose. Crank the learning rate and watch it forget. Drop the epics and watch it learn slow. Feeling the failures is how the numbers finally make sense. The free notebook is in the bio. Okay, big one today. They'll ask you to walk through a single step of RLHF training, start to finish. And the people who fumble it just list buzzwords. Let's actually trace what happens in order and why. Here's the whole loop in one breath. The model writes some answers, you score them, you figure out which choices were better or worse than expected, and you nudge the model toward the better ones. Everything else is detail on that skeleton. Step 1, you grab a batch of prompts from your dataset. Just questions or instructions, the raw material for this round. Nothing fancy yet, you're setting up the practice questions. Step 2, the current model, the policy, writes answers to those prompts. This is the model trying its best with what it knows right now. And heads up, this generation step is the slow part of the whole thing. Step 3, you hand every answer to the reward model, and it spits out a score, how much a human would probably like this one. That score is the only signal telling the model what good even looks like. Step 4 is the clever bit. A raw score alone isn't that useful. What you really want is, was this answer better or worse than you expected? That gap is called the advantage, and you estimate it with a method named G. A E positive means pleasant surprise, push toward it. Step 5, you update the model using PPO with what's called a clipped objective. The clip is a safety rail. It stops any single update from yanking the model too far in one go. Small, careful steps beat one reckless leap. Step 6, you also update a little helper called the value function. Its whole job is to predict how much reward to expect, and that prediction is exactly what Step 4 leaned on. So you keep sharpening it as you go. Step 7, the guardrail. You measure how far the model has drifted from its frozen reference using KL divergence, and you subtract a penalty for drifting too much. Skip this and the model happily hacks the reward. This is what keeps it honest. And then you just do that again, and again, thousands of times. Each loop the model writes gets scored, gets gently corrected. That slow grind is how a decent model becomes a genuinely helpful one. Anyone can rattle off the 7 steps. The person who gets the offer explains why you use advantages instead of raw reward, and what the clipping and the KL term are protecting against. That's reciting it versus owning it. So go code this loop end to end and watch the reward creep up step by step. Once you've built it once, you'll never forget the order. The free notebook is in the bio. So this one sounds backwards at first. In PPO, the reinforcement learning method behind a lot of RLHF, you actually pay the model a little bonus for staying uncertain. Why would you reward not being sure? That's the whole question today. First, the word. Entropy here just measures how spread out the model's choices are. High entropy means it's keeping lots of options on the table. Low entropy means it's basically always picking the same thing. Think of it as how open-minded the policy is at each step. And here's the failure it's guarding against. Early in training, the model stumbles onto one decent answer, gets rewarded, and immediately doubles down. It collapses onto that one move and stops trying anything else. It locks in way too soon before it's explored what else might be better. That's premature convergence, and it's a real trap. So picture someone who finds one okay dish at a restaurant and orders it every single visit forever. They'll never discover the thing they'd actually love. The entropy bonus is the nudge that says, hey, keep sampling the menu a little longer before you commit. Mechanically, it's gentle. You add the policy's entropy right into the training objective, so the model gets a tiny reward just for keeping its options open. That pushes back against collapsing to one answer. It's a thumb on the scale towards staying curious. And the strength is a knob, usually set tiny, around 0.01, small on purpose. You want a light breeze toward exploring, not a gale. Too big and the model just babbles randomly. So it's a gentle, steady nudge, not a shove. And in RLHF specifically, this is what keeps your model from going flat. Without it, you can end up with a chatbot that answers everything in the same dull, samey way. The entropy bonus helps it hold onto variety, so it still feels alive instead of one note. And here's the offer-getter. Anyone can say the entropy bonus encourages exploration. The hired answer names the exact failure it prevents. Without it, the policy collapses to one deterministic answer too early, and in RLHF you lose response diversity. Naming the collapse is what lands it. So go run PPO with the bonus and without it, and watch one version stay varied while the other collapses to a single answer. That contrast makes it stick. The free notebook's in the bio. So here's a sneaky problem in RLHF. Your reward scores keep drifting around as the model improves, and that drift can quietly destabilize the whole training run. Reward normalization is the fix. They ask how it works because it tells them you've actually run this thing. Let's get it. Here's the issue. Early on, a decent answer might score a 2. Later, when the policy's much better, an average answer scores a 10. The scale won't sit still. So the same update means totally different things at different times, and your training gets jumpy and unstable, moving goalposts. So the move is to grade on a curve. Instead of caring about the raw number, you ask, how does this answer compare to the batch around it? Above average or below? That comparison stays meaningful even as everyone's raw scores climb. Relative, not absolute. And the recipe is the classic one. Take each reward, subtract the running mean so the average sits at 0, then divide by the running standard deviation so the spread is consistent. Above average rewards go positive, below average go negative, all on a steady scale. Center it, then size it. And the running part matters. You don't freeze the mean and spread once. You keep updating them as training rolls on. So as the policy improves and the raw scores creep up, your yardstick quietly moves with them. The signal stays calibrated to right now, not to where you started. And that's the payoff. The reward signal now lives on a consistent, well-behaved scale no matter how good the policy gets. Updates stay sane, the gradients stay calm, and the run just stays stable. That's the whole point. Steady signal, steady training. And a little extra you can mention. Some setups also clip the rewards, capping them to a range like -5 to +5. That just stops one freak outlier score from yanking the whole update around. A seatbelt on top of the normalizing. Nice detail to drop. And here's the offer-getter. Anyone can say you subtract the mean and divide by the standard deviation. The hired answer says why it's running. As the policy improves, the reward scale drifts, so you track the stats live to keep the signal stable and you clip outliers. That why is what lands it. So go train with raw rewards, then with normalized ones and watch the jumpy runs settle right down. That contrast is the whole lesson. The free notebook's in the bio.